So now we're going to talk about angular and translational quantities. So we've already said that if you have a particle, so if this is my x direction and this is my y direction here, and I have a particle that is rotating, and let's say that the distance from here to here is the radius, and this is my angle theta, then I know that I can write the arc length s. So the displacement from this point to this point is called the arc length, and this arc length is given by s, which is equal to the radius times the angle theta. So if I want to find this, it's called the tangential velocity. So if you want to calculate this tangential velocity, what you're going to do is that you take the derivative of s with respect to time. So if you take this derivative here, now if we assume that the radius is not changing, so if the radius is not changing, it means that when I take the derivative of s with respect to time, you just get r times d theta by dt. And if you plug in these values, because we know that d theta by dt is equals to omega, then I get v is equals to r times omega. So this tells me how the angular velocity omega is related to the tangential velocity v. So it's just to multiply by the radius. So angular speed, tangential speed are related by means of this equation right here. Now let's look at acceleration. So we can calculate the tangential acceleration by taking the derivative of the velocity with respect to time. But we know that the velocity, the tangential velocity, is given by the radius times the omega. So if you substitute this value here again, if we said that the radius is constant, so if you pull out the radius out of this derivative and just take the derivative here, you get a tangential is equal to r times the omega times dt. But we know that the omega by dt is equal to alpha, so you get the a tangential is equal to r times alpha. Now we also know that when an object is moving in a circle, in addition to the tangential acceleration, there is also an acceleration that is pointing toward the center, which is called the centripetal acceleration. And this centripetal acceleration, is also called the radial acceleration. So the radial acceleration is just given by v squared over r. And because we know that v is equals to r times omega, if you plug that in also, you can get a centripetal is equals to r times omega squared. So now we can see that I can write the total acceleration vector. It has two components. There is the tangential component as well as the radial component. So if you add these two vectors up together, you get the total acceleration vector is pointing in this direction. So this vector is just the sum of these two vectors right here. So I can write the total acceleration vector as the tangential acceleration vector plus the radial acceleration vector. Now, because we can also calculate what the magnitude of my acceleration vector is given by the square of the tangential acceleration plus the square of the radial acceleration, square root of all of that quantity. You end up with this, which we can also write as r square root of alpha squared plus omega raised to the power of 4. All right. Now, this is quick quiz number 10.3, part 1 again. I'll just let you guys, I want you guys to take a look at this quiz, as well as you can also take a look at part 2. So now we're going to move on to talk about a quantity that is called the torque. So generally what the torque is all about, if you remember, we said that we need to apply a force for an object to move in the x direction. For translational motion to take place, we need to apply a force. So similarly, for rotational motion to take place, we need to apply a torque. Now, a torque is simply defined as so the torque is the perpendicular value. So if you take the force, if this force is applied at some angle, then we need to take this force and write it into x and y components. So if you notice that in this example right here, if you look at this range, so this point here is called my axis of rotation. So when I calculate the torque, I only need to use the component of the force that makes 90 degrees with respect to the direction of my radial vector, the radius vector. So when I calculate the torque, I must use only the component that is at 90 degrees with respect to this. So there is a 90 degrees angle between the direction of this component and the direction of my displacement. So you can see that there is a 90 degrees angle right here. So this is not going to give me any component. So I can only use the component that is perpendicular. It's a 90 degrees with respect to the direction of this displacement vector. So you can see that the torque in this example is given by this. It's just the y component of the force multiplied by the distance. So the distance here is the distance from the axis. So we can write this as F times D. All right. Now, so generally, so there is two types of torques. So suppose that we have an object here, and there is two forces acting on it. There is F1 acting in some direction, and there is F2 that is acting at some direction as well. And let this point be the point where the object is going to rotate. Then we're going to see that F1 is going to produce a positive torque. So F1 is going to rotate this object in the counterclockwise direction. So remember we said that counterclockwise is the positive direction, while F2 is going to rotate this object in the clockwise direction. So when I calculate the net torque, the sum of all the torque, so this symbol here tells me the sum of all the torque, is the torque from force number 1 plus the torque from force number 2. Now notice that force number 1 produces a positive torque because this is in the counterclockwise direction, while torque number 2 is in the clockwise direction. So when I calculate the sum of all the torque, I must put a negative sign here. And the reason why we put a negative sign is because F2 produced a torque that is going to cause this object to rotate in the clockwise direction. So again, the key point that you want to remember here is that there is two types of torques. There is a counterclockwise torque, which is considered the positive torque, and there is a clockwise torque, which is the negative torque. All right, so now we're going to look at example number 10.3. And in this example here, we're going to calculate the net torque on a cylinder. So suppose that you want to calculate the net torque on the cylinder as shown in this picture right here. So we have, so there is, so you can see that in this cylinder here, so R1 is the outer radius and R2 is the inner radius. So there is a tension force T1 that is applied at this point, and there is a tension force T2 that is applied at this point right here. So again, because this point is my axis of rotation, so notice that this force is, again, this is at 90 degrees with respect to my axis. So when I calculate the torque, the only thing that I need to remember is that T1 is going to be in the clockwise direction, so this would be a negative torque. Meanwhile, T2 is going to produce a counterclockwise torque that is pointing in this counterclockwise direction. So when I calculate the net torque, you're going to see that it's just given by R2 times T2 minus R1 times T1. Again, the reason why this is negative is because T1 is going to produce a torque that is going to be pointing in the clockwise direction. So again, clockwise is negative, counterclockwise is positive. So T2 produces a counterclockwise torque, so this is considered positive. Now suppose that T1 is equals to 5.00 newtons, R1 is equals to 1.00 meters, and T2 is equals to 15 newtons. and R2 equals to 0.50 meters. Then we can go ahead and just substitute the value here to calculate our net torque. So if you plug in all those values here, you get 2.5 Newton meters. So again, the unit for measuring torque is Newton meters because um, distance is in meters and force is in newtons. And so torque is just the product of force times distance. So it means that this will be in units called Newton meters. Then it's going to also ask us which way does the cylinder rotate starting from rest. So again, we notice that this is going to rotate in the counterclockwise direction because the torque is positive. So because the net torque is positive, it means that the cylinder is going to rotate in the counterclockwise direction. All right. Now we're going to start talking about analysis of a system of a rigid object under a net torque. So basically we said that if you have a mass that is moving in a circle, and let's say the distance from here to here is r, we've already said that there is two types of acceleration. There is an acceleration that's pointing towards the center. This is called the radial acceleration. And there's an acceleration that is pointing in this direction that is called the tangential acceleration. So it means that I can write down Newton's laws for the radial as well as the tangential acceleration. So for example, we know that the sum of all the forces is equals to mass times acceleration. So in the tangential direction, I can say that the sum of all the torque is equals to tangential force times the distance. So again, we know what the distance from here to here is. So you get the sum of all the torque is just equals to the sum of the tangential force times the radius, which is m times at times r. And so because we know that the tangential acceleration is given by r times alpha, so if you substitute all this quantity right here, we can write the sum of all the torque as mr squared times alpha, which we can also rewrite this equation as this, where so this I is a quantity that is given by mr squared. It's called the moment of inertia. So we're going to talk a little bit more about this. Now notice that when I calculate the net torque, the radial component does not give me any contribution, because remember that I only need the component that makes 90 degrees with respect to my distance. So because the radial component is pointing in a direction that is parallel to the radius, this will not give me any contribution to the torque. All right. Now, if you consider an object that is moving in a circle, then because this object here is called a rigid object, so what we can do is that we can take this object and chop it into smaller masses called mi, and so I can write down Newton's laws for each of these ith masses. I can say that the force on particle number I is equal to mi times ai. Then I can calculate the torque on particle number I is equal to ri times fi, which is just given by ri times miai. And then if you substitute the relationship between the tangential acceleration and the angular acceleration, we can write the torque as given by this equation right here. Now, if I want to calculate the sum of all the torque, I must sum all the contributions that come from each of the individual mi's, the masses. And so if you do that, you end up with an equation that looks like this. So basically, we can write Newton's law for rotational motion as the sum of all the torque is equals to I times alpha, where I is given by this quantity right here. So this quantity is called the moment of inertia. So the I value is called the moment of inertia, and this is something that we're going to discuss a little bit more about just to show you how this can be used to solve problems.